Okay, so we're going to pick up chapter 15 today. We talked a lot about chapter 14 in the last lecture, where we looked at Mendel and his gene idea. Today we're really going to focus on and pick up chapter 15, which is the chromosomal basis of inheritance. So we're going to talk more about what happens in meiosis, what happens in those gametes and the sex cells. And we will do, again, a lot of practice problems for this in class. I'm not going to go through all the practice problems here in the lecture, but we will be doing those in class, so it is imperative that you come to class for these chapters to get the practice that you need. Before we get into doing the talking about the inheritance of genes on the X chromosome and through those sex cells, I want to talk a little bit about probability and a couple of tools that you can use to help you as we go through and do some of these problems. When we talk about genetic ratios, and I think you'll remember this from chapter 14 lecture, we talk about genetic ratios in terms of probabilities. What is the expected frequency for an event to occur? So we can think about this in two possible ways. If an event is absolutely certain to occur, then the probability is 1. So if we know for 100% fact chance that something is going to happen, then we know that probability is 1. If the event is absolutely certain not to occur, then the probability is 0. And when we talk about genetic ratios or genetic probabilities, we're somewhere in between that. We're always going to be somewhere, well, not always, but we're most of the time going to be somewhere in between. So we're going to be talking about probabilities of somewhere between 0% or 100%. When we talk about monohybrid crosses, there are some specific ratios that we can use to help us automatically know what the phenotype of the offsprings is going to be. So when we talk about monohybrid crosses, the expected ratio of a dominant and a recessive phenotype is 3-1. So what that means is if we were to cross two hets, so if we have two organisms that are heterozygous for this gene, and let's say we're talking about fur. So big A represents long fur, and little a represents short fur. And so we have, in our parent generation, we have two organisms that are heterozygous for this trait. So when we get ready to do the Punnett square for these organisms, we put the possible gametes for one organism on the top, the possible gametes for the other organism down here on the bottom, and then we fill in the square. So that one would be big A, this one would be big A, little a, little a, and then little a, little a. So we have 4 possibilities of outcomes here, 4 possible different genotypes that we could see. And so in this case, we have a 3 out of 4 chance, or 3/4, or 75% of a dominant phenotype. So in this case, our dominant phenotype was long fur. So that means we have to have at least one big A. So we have 1, 2, 3 of our 4 offsprings would have a dominant phenotype. We'd have 1 in 4 chance, or 25%, of a recessive phenotype. So our recessive phenotype here is short fur, so only 1 out of our 4 offspring would have the possibility of a recessive phenotype. We call this then a 3-1 ratio. So 3 dominants to 1 recessive. That is our ratio. We can also talk about genotypic ratios here. So when we're looking at the genotypes, remember that is the letters that are expressed. And in this case, we have 3 possible genotypes. We have big A, we have big A, and we have little a, little a. Those are our genotypes from our possible genotypes from the cross of these 2 hets. So in this case, we actually have So we still have our 4 possibilities. So we'll put that on the bottom. And then for big A, we have one of our offspring has a big A, or 25%. We have 2 of our offspring that have big A, so that's 2/4 or 1/2 or 50%. And then we have that one offspring that is a. So our genotypic ratio when we cross hets, we say is 1 to 2 to 1. So 1 homozygous dominant to 2 heterozygous to 2 homozygous recessive. All right, so when we are thinking about probabilities, we have 2 different rules that we can use to help us. And we're going to use the example of tossing a coin here when we're thinking about how to use these rules. So the first rule is the product rule, and this predicts the combined possibilities of independent events. So what that means is that one event, the outcome of one event is not going to affect the outcome of the second event. So in words, this says the probability of 2 independent events occurring together can be calculated by multiplying the probabilities of each event occurring separately. So we'll go through an example of. So here we have a coin toss, and we toss this coin twice. So in our first toss, we have a 1/2 probability of getting heads and a 1/2 probability of getting tails. So we're going to toss that coin once. There are 2 options. Then we have the second toss, and again, we're going to have a 1/2 probability of getting heads and a 1/2 probability of getting tails. Now, these events are independent. What if I get heads or tails on the first toss? That has absolutely no effect on whether I would get heads or tails on the second toss. So these are independent events. That is when we use the product rule, because the events are independent. And so if I were to ask you, what is the probability of getting what is the probability of landing on heads on the first toss and landing on heads on the second toss? Well, we would look at this square right here. So the probability of getting heads the first time is 1/2. The probability of getting heads the second time is 1/2. And because this is the product rule, because they are independent events, we multiply those things. So when we multiply 1/2 times 1/2, we get 1/4. The key to the product rule is the word and. If you see the word and in a question, you know automatically you're going to be using the product rule. So if I were to ask this question, I might say, what's the probability of landing on a tails on the first toss and getting a tails on the second half? Well, again, that would be 1/2 times 1/2 to give us 1/4. Now, the second rule that we can use is called the sum rule. The sum rule predicts the combined probabilities of mutually exclusive events. So what that means, if one occurs, the other cannot. So these are not independent. The outcome of one event is going to affect the outcome of the second event. So, for example, this would be, there are 2 different ways that heterozygous parents could have a heterozygous child. And I'm going to show you an example of this in just a second. But again, in words, the sum rule says the probability of an outcome that can be obtained in more than one way can be calculated by adding the separate probabilities. So, okay, here we have an example for the sum rule. It says, what are the chances that a family with 2 children will have 1 boy and 1 girl? Well, there are a couple of different ways that we could get 1 boy and 1 girl in a family. We could have the first child be a girl and the second child be a boy, so that could happen. We could have the first child be a boy and the second child could be a girl, so that could also happen. So the probabilities here, if we think about this first option here, so what is the probability that the first child is a girl? Well, that's 1/2. What is the probability that the second child is a boy? Well, that's 1/2. So if we're thinking about just this event, so we would have to, in order to get this, our first child would have to be a girl and our second child would have to be a boy. So I said and, so I'm going to multiply So that is 1/4. So the probability of this event happening is 1/4. Now, if we look at the second way we could get a boy and a girl, we would say that our first child is a boy. So that would give us 1/2. We'd have a 1/2 chance of having a boy. The second child being a girl, again, that would be a 1/2 chance that our second child would be a girl. So then, if for this event to happen, the second event to happen, our first child would have to be a boy and our second child would have to be a girl. So we would multiply those and get 1/4. Now, for this particular example, for the sum rule, we could have either of these things happen that would lead us to one boy and one girl. So the two ways that we could get a family with two children to have a boy and a girl is event one could happen. We could have the first child be a girl and the second child be a boy. Or we could have this second event happen where the first child is a boy and the second child is a girl. So when we have ors, we add those probabilities. So 1/4 plus 1/4 in this case is 1/2. So the probability of a family with two children having one boy and one girl is 50%. The key for the sum rule is anytime you use this word or, that's an indicator that you're going to add the probabilities. All right, so let's talk about the types of chromosomes in your body. We have talked a lot about the autosomes in chapter 14. These are the somatic cells. You have 22 pairs of autosomes. These are the same in both sexes, and these are your body cells. The ones that we're going to focus on today in chapter 15 are the sex chromosomes. So these are the chromosomes that determine an individual's sex, and humans have one pair of sex chromosomes. That should say sex chromosomes, not autosomes. Forgive that error. So humans have one pair of sex chromosomes, so we're going to look at what those are. All right, so here's an example of all of the chromosomes in your body. Again, your body cells are diploid, so they are what we call 2N. You have 22 pairs of autosomes. Those are the ones that are the same in both sexes. And then you have one pair of sex chromosomes. So if you are a female, your sex chromosomes are XX. If you are a male, your sex chromosomes are XY. So that's how we represent males and females in terms of our chromosomes. Remember, in the gametes, we only have haploid cells. Remember, our gametes are haploid. So we have 22 autosomes instead of pairs. We only have the 22 autosomes and then one sex chromosome. So your gametes, if you're a female, all of your gametes have an X chromosome. If you are a male, your gametes can have an X or a Y sex chromosome. Okay, so this is what we call a human karyotype. This is a picture of the chromosomes taken during mitosis and then paired up based on their homologous pairs. So we base that on size, centromere location, and banding pattern. So you can see these are our sex chromosomes down here. So if we are a female, we are XX. If we are a male, we are XY. Okay, so remember pairs 1 through 22. These are what we call the autosomes. These are the same in both sexes. And then that 23rd pair, those are the sex chromosomes. That determines whether you are male or female. Okay, so how do we determine this when parents have offspring? So when two parents have a child, how do we determine whether we are going to have a male or a female? Well, if you are a female, all of your gametes have an X chromosome. So females only have X's. So every single one of your every single one of your eggs carries an X chromosome. So in females, you only have one option for your gamete, and that is an X. In males, your sperm could have either an X chromosome or a Y chromosome. So if we were doing our Punnett square here, we would put both of those gametes along the side. And then we can fill in the boxes. If it is an X sperm that fertilizes the egg, we end up with an XX, and we would get a female child. If it is a Y sperm that fertilizes the egg, we end up with an XY, and we would get a male child. So it is the father who determines the sex of the offspring. Okay, so when we think about the way that genetics works, so here we have a autosomal recessive trait that we're passing down. So this is what we call autosomal, remember. So that tells us that this is not on the sex chromosome. This tells us that this gene is located on the autosomes, which again are the same in both sexes. So if we have a normal mother, so she is an AA, lowercase a. She is not affected by this condition at all. She's perfectly normal. So during meiosis, her gametes are going to form, and she's going to give us either an A or, both of her eggs would have little a, little a. In the male, he is going to have the genotype big A, little a, so he is affected by this trait. And so it's a dominant trait, so he is affected. So because he has the dominant allele, he is going to express this trait, whatever it is. And so during gamete formation during meiosis, he has two possible gametes that can form. He's going to give us the big A, or he's going to give us the little a. And so when we look at the children that are affected, again, we can fill out our Punnett square. We're going to have a 50% chance of having an affected child and a 50% chance of having a normal child. So that is it. This is just like what we've been talking about in chapter 14 as far as filling out the Punnett square and calculating the probabilities. Now, it's a little bit different when we talk about recessive traits. So these are going to be genes that are only expressed if we have two of the alleles. So if we're talking about recessive traits, we get a little bit different situation here that we have to consider. So we get what are called carriers. So in this case, mother and father are both carriers of this trait. So they have the little a allele, but neither one of them express it because they also have the big A allele, which masks or is dominant over the little a. So when the mother produces her gametes during meiosis, she can give us a big A or a little a, and same thing with father. He's got big A and little a, so he can give us big A or little a. So now when we fill out the Punnett square, we get big A here, big A, little a, or little a, little a. So our big A child is normal. We don't have to worry about her. She doesn't have the recessive allele to pass down, or him rather, whatever it is. Then we have the probability of half of our offspring being carriers. So just like their parents, they have that lowercase, that recessive allele, but they also have the dominant allele, which masks it or hides it. So while they do not express this particular trait, they are a carrier and they can pass it down to their children. Now, we have a 1/4 chance, so 1 out of 4, of having an affected child that does express this trait. So this child is not considered a carrier. This child is considered affected because they have 2 copies of that recessive allele, and therefore they would express this trait. Now, when we talk about X-linked recessive inheritance, we have a couple of things that we consider. So there are 3 things that happen with X-linked recessive inheritance. Number 1 is X-linked traits are more common in males than females. Number 2, males inherit their X-linked disorders from their mother. And number 3, all carriers of X-linked traits are female. So we are going to discuss these 3 issues in class. And I want you to be thinking about why these things are true for X-linked recessive inheritance. So this is something that we are going to talk about extensively in class and that you have to have a good understanding of. So I want you to be thinking about this before class next time. All right, so one last thing, if we are looking at inheritance through the sex-linked gene or through the X-linked gene. So by the way, when we talk about sex-linked genes, we're always talking about genes on that X chromosome. They're really nothing important on that Y chromosome. And so we almost never talk about Y-linked inheritance because females don't have a Y. So there's nothing important on that Y, I always tell people. All right, so if we have an X-linked trait, so again, this is something that is only going to be on the X chromosome. So we have a carrier mother. So again, this mother has the X-linked trait on one of her X chromosomes, but she also has a normal X chromosome that's going to mask the trait. So she is not affected by this gene, but she is a carrier. So her eggs can be either normal X or affected X. So the offspring or the gametes that she passes down to her offspring could be normal, or they could have that carrier affected X. Now we have a normal father, so his X is going to be normal, and then his other chromosome is going to be the Y, which again has nothing important on it. So that's a normal gamete that he could pass down, and then he could have his normal X. So when we fill in the Punnett square, we have normal X, so that's a daughter. We have normal X, normal Y, so that's our normal son. We could get this affected X from mom and our normal X from dad. So this is a carrier daughter. So again, she's not going to be affected by this trait, but she is going to be a carrier. She could pass it down to her children. So she has this dominant or this normal X that is masking or covering up the affected X. Now, this guy here, so he got the affected X from his mother and a normal Y from his father, so he is affected. He doesn't have another X chromosome to mask the affected X, so he is going to be expressing whatever this gene is and be affected by whatever condition this gene causes. So this is X-linked inheritance. We have to think about carriers versus normal versus affected offspring. So again, we're going to do a lot more examples of this in class in the coming weeks. So be sure you attend class in the next few class periods so that you get to do all the practice for these genetic problems that you need before the next exam. See you in class.